I'd like to thank you, Luke, for inviting me for this talk. It's always difficult to give a talk of this nature because, you know, the audience has such a big, wide range going from sixth formers all the way up to professors. So I've tried my best to you know, include material both which is fairly introductory and a little bit also advanced. So let me share this mathematical notebook with you. What are eigenvalues? So we already had an introduction about eigenvalues, and the important thing about eigenvalues is that it captures important numerical aspects about matrices. What I'm going to say here, however, is first that I'm going to see the limitations. I'm going to show the limitations of eigenvalues first. So imagine we take a matrix A consisting of these values here. So most values are 0, except that there are these ones on just above the main diagonal. So the main diagonal is the one starting from the top left corner there all the way down the bottom right. So those are all zeros, but above it we have all ones. Okay, so let's define this matrix A. It's going to take some time before it does this. But as you can see, those of you who have already done a little bit of matrices, whenever you have a matrix which is upper triangular, such as this one, right? Every number below the main diagonal is 0, then you can simply read off the eigenvalues because they're simply the values on the main diagonal. Okay, so in this case, they are all 0. And if you input here eigenvalues A, you'll find a confirmation of this. All the eigenvalues are 0, right? But I want to show you that this is not, it gives you a misleading picture of this matrix A. And to do that, I'm going to input the vector consisting of all ones, right? So we don't expect anything strange to happen because, as you can see here, the eigenvalues are all 0. But if I do this, you can see from here that if you apply the matrix A to this vector X, the output looks very much similar to this input vector, right? It consists of all ones except for this very last position here, which is 0. So even though 1 is not an eigenvalue, right? In this case, we have AX is almost 1x, right? So this matrix, which doesn't have 1 as an eigenvalue, yet, however, it is almost an eigenvalue. And this is not just true for the number 1. If you input this vector, 1, r squared, and so on, all the way up to r to the 11 in this case, because I can't keep on going. But if you, again, do the same multiplication of this matrix A with this vector X, well, the output is going to be r, almost as you can see here, r times the input vector. So AX is r times x. Well, again, not exactly, of course, because there's this 0 here, and that would not be true, but almost true, right? The output vector is almost r times the input vector. So that means the value r is, let's say, almost an eigenvalue of this matrix. And perhaps I can make this a little bit more visual so that you can easily see what's happening here. So in this matrix, I'm going to represent the values here with actual white for 0 and black for 1. And similarly for these values here, they're going to have gray values. So you can see from here, this is the same picture as I had previously, essentially. So you have this matrix applied to this vector. When you multiply them out, you get this output vector. And as you can see, especially on Zoom here, which doesn't actually make these colors too faithful, so to speak, you can see that this input vector and this output vector are practically almost the same. And of course, you can see that this will happen, this will be even truer if you pick larger and larger matrices. So although, as you will see, both in the previous talks and also in the following ones, eigenvalues are extremely important, right? Because they capture a lot of information about matrices, right? Yet, on the other hand, eigenvalues have their limitations. And as you can see, this is one of the limitations, that although officially this matrix has only zeros as eigenvalues, but yet, as you're seeing over here, it does have almost eigenvalues. And this is to make this rigorous, really, what you need to do is you need to go to infinite dimensions. There's no way of capturing these other values, these almost eigenvalues, so to speak, without going to infinity. And this is my favorite example. When you look up, today you can, search anything you like on the internet, and you'll find all sorts of videos, for example, on YouTube. And last time I was watching one saying that, all this talk about infinity doesn't make sense, especially coming from computer scientists, I find, because there's this philosophy, so to speak, that everything should be discrete. If you go to infinity, then you don't really know what you're doing. But and in a sense, that's true. That's the Greek way of talking about it. And avoid anything to do with infinity because we're living in a finite world. But this is my favorite example here, that actually infinity does help us think even about finite things. Here we have a finite object made up of a finite number of columns and rows, and all the mathematical setup that gives us the eigenvalues only show up 0 as an eigenvalue, whereas in fact, if you go to infinity, you'll find that there are in fact these other extra almost eigenvalues. Now, what do I mean by going to infinity? Now, I want to make sure. What do I mean by going to infinity? Well, we can go to infinity in two different ways. One way is to make these discrete changes in values here finer and finer. So imagine you take finer and finer values, you might end up with something like this. So matrices which have a huge number of rows and columns, but which give up kind of similar to this one, where you have white being 0 and black being 1. Here you have intermediate values like this, and you can visualize this as in the following way. And this matrix being multiplied with this vector, again, this is a vector with a large number of components, right? When you multiply them out, you end up with this right-hand vector. So my favorite way of thinking about matrix multiplication is to take a vector, think of it as applying it horizontally like this at the top, and then multiplying out the corresponding values with each other. And whatever number comes out, you'll write it down, you'll put it down on the right-hand side. So as this horizontal vector of this form here is being scanned down these rows, you're going to end up with different values over here. Now you can see what's going to happen here, that if you take this to the limit, then instead of having discrete rows and columns, you end up with a whole function, right? A function of x and y. So essentially, this is what you have. You have previously, we had a multiplication of a matrix with a vector written in this form here and outputting another vector. But whereas if you were to refine this, as I was saying, and take the limit, where these I and j now become real numbers now, let's say between 0 and 1, as you go from one end to the other end of the row, then instead of a summation, you end up with an integral, okay? So ij become xy, and this vj here becomes some function of y, that's this vertical function now. And the output of this integration becomes this vector here, which is another function of x, right? So in the limit, this is what happens. And you've already seen this, however, in one way or another. For example, when you consider the Fourier transform, especially those of you who have done this in the first year at university, well, the Fourier transform is a special case of this, right? Where you have an integral with an exponential function here, and you input some function and the output is some other function. Okay? Now, you see, so what I was trying to say before is that if you try to work out the eigenvalues of a discrete matrix that misses out these approximate eigenvalues, and that would be very important if, for example, you take some continuous problem and you discretize it and then try to find its eigenvalues, that's going to miss out on the true eigenvalues of this continuous case. And now there's another way which we can go to infinity. So that's one way. Another way is to, instead of refining the values, you take more and more values, right? So instead of having a finite vector like this, you can take an infinite vector by keep adding more and more components. And then a matrix can also generalize in this way by having an infinite number of columns and an infinite number of rows, right? It's still discrete, unlike this case, but it would have an infinite number of columns and rows. But again, even in this case, you're already familiar with this. This is nothing new, actually. Because if you take any function f of x and you write down its Taylor series, or its Maclaurin series in this case, right, as a sequence, a series of terms involving x, x squared, and so on, and that every function will have its own coefficients, an. Now, if you take those coefficients and you write them down as a vector, this vector will incorporate in it the most important information about this function f. Right? And it's actually a very convenient way of representing the function, because whereas a function of x has an infinite number of values, so to speak, right? As you change x, f of x changes with x, so you have an infinite number, so to speak, of information, you might think. But actually, if you represent it in this way, what you need are a discrete set of numbers here. Okay? So this vector, of course, you have to cut off at some point to make it fit into this program here, but think of it as an infinite vector. So this infinite vector represents this function f. And it represents it in very interesting ways, because even if you take, let's say, two functions and you add them up together, what will happen to the corresponding vectors? So for example, suppose you have a function f and you represent it, and its Taylor series would be, let's say, this bracket here. And then you have some other function g represented by some other Taylor series like this, and you add them up together and perhaps even multiply one of them by some scalar, then what will happen to the vector representing that sum? Well, let's see, let's input this into Mathematica. So I've added up these two vectors together, and now Mathematica leaves them separate. So let's collect the terms with x, and as you can see now, we have a new component here, the zeroth component. Then you have the one component multiplied with x and so on. And as you can see, what's happening here is that the column vector representing f plus 2g is exactly the same as what you would get if you take the vector representing f plus twice the vector representing g. Right? So it's not a simple, it's not just a convenient way of writing a function. It's what happens to the vectors relates precisely to what happens to the functions. So to write it down more formally, if you add two functions together, it's as if you're adding its vectors to get their vectors together. And if you multiply a function by a scalar, it's as if you're multiplying the vector by that scalar. You might say, but you can do more stuff with functions than you can do with vectors. And that would be true, right? You can multiply functions together, but you cannot kind of multiply vectors together. But depending on the correspondence that you're using, if you multiply two functions together, actually, you'll see that it corresponds to what's called the convolution of those two vectors. And there's another thing that you can also, I should say here that this is not the only way of creating vectors from functions. You can use, for example, the Fourier series, or there are, of course, many, many different ways of coming up with components that represent functions. Another thing that you can do to functions that you can't normally do to vectors is differentiation. You can easily differentiate a function, but what on earth does differentiating a vector really mean, right? Well, let's see what happens when you take a function written in this way as a Taylor series and you differentiate it with respect to x. Well, you're going to end up with another vector, so to speak, right? If you look at these components. And really what's happening is that you have some kind of matrix applied to the original vector, and the output vector will represent the derivative of f. So essentially, differentiation is really just a matrix, right? It's an infinite matrix, so to speak, okay? An infinite matrix with an infinite number of columns and rows whose values are all 0, except those on the top diagonal here, whose values are just the integers. Right? Now, of course, it would be interesting, therefore, to tie up with what we were saying about eigenvalues, to think about what are the eigenvalues of this differentiation operator, right? Again, if you restrict yourself to traditional, to how eigenvalues are defined, you would be misled into thinking that the eigenvalues are just all 0. Okay? But you know that that's not true, because you've done this also at A level. There are functions such that when you differentiate a function, the output is lambda times that function. Okay, so think of these functions as these vectors. So f of x is this vector here. Then the derivative operator is this matrix. And we're looking for a special function, a special vector, such that when you differentiate that vector in this sense, the output is going to be some scalar times the original vector. Well, if you solve this algebraically, you'll get nothing, right? There are no functions which satisfy like this if you restrict yourself to vectors in this form. But if you think about the differentiation and you think of this as a differential equation, you can solve this equation, and you know the answer to this. It is the solutions to this equation are exponential functions, right? E to the lambda x. And you can verify this easily using Mathematica here. If you differentiate e to the lambda x, the output is lambda e to the lambda x. Right? So actually, differentiation does have eigenvalues, and those eigenvalues are not represented by this diagonal here, right? So there's this difference between what happens in the finite case and what happens in the infinite case, right? Now, to really, to bridge this gap between what's happening in the finite case and what's happening in the infinite case, you have to go to the gist of eigenvalues. And the gist, I think, is this one here. What eigenvalues really show is when is this equation a minus lambda I times x equal to b, when do things go wrong with that equation? Well, normally, you can invert this matrix, take it on this side, and for every vector b, you can find the corresponding vector x. Now, what would we like this solution, what kind of properties would we like this sort of equation to have, to satisfy? Well, we would normally want the solution to exist. We would want the solution to be unique, and we would want the solution to be stable. Stable in the sense that if you change b slightly by 0.01 or some small value, then you would want the starting vector here, x, to also change just slightly. Now, eigenvalues are those special values for which this breaks down, okay, for which you don't have a solution which is, and either it's not unique or it's not stable. Now, it just happens that in finite dimensions, right, finite matrices like this, these three things go together. Either a matrix has solutions which are unique, which are stable, or they don't, right? But in infinite dimensions, these three things are different from each other. They're different concepts. So you might have, well, let's call them not eigenvalues anymore. Now we call them spectral values. There are spectral values for which the solution does not exist. There are spectral values for which solutions exist but are not unique. In fact, these are the eigenvalues. We still call these eigenvalues. And then there are spectral values for which solutions exist and are unique, but they're not stable. Right? So this is the generalization that we get when you go to infinite dimensions. So I was talking about before about the eigenvalues of the differentiation operator. Let's do this twice, actually. Let's take two derivatives. Someone asked the question before, why do we put the I complex number with the derivative operator? Well, the answer is that the differentiation really acts a lot like an imaginary number, in the sense that when you differentiate twice, it is really very much akin to having a negative number, right? So we say that two derivatives is actually negative. We call this a negative operator. So one derivative is really like an imaginary number, so to speak. And that is why we, in Professor Ashwirap's talk, when you had d by dt there, that derivative, you multiply it by I to make it into a real operator, okay? So that you can have real values coming out. And this explains also why, what I'm going to write here, I put a minus sign before this y double prime, so that this negative operator with this minus sign becomes a positive operator. You know, we like positive numbers more than negative numbers mostly, so we do this sort of thing. And we can ask, therefore, what are the eigenvalues of this minus y double prime? Okay, so what are the solutions of this equation? Now, I was saying before that, you know, eigenvalues need to be generalized to spectral values. But actually, there is a whole set of operators, including differential operators, for which eigenvalues still are the most important things. And you don't get anything much new, let's say, with spectral values. And these are called compact operators. And these actually crop up in a lot of differential equations when you have something like this with bounded conditions, boundary conditions. So let's say take y of 0 is 0 and y of 1 is 0. So you're only interested in the interval between 0 and 1. Well, when you solve this equation, the solutions are going to be sine n pi x, right? You can solve this equation, right, using A-level mathematics, and you get these sine functions. And now they look a little bit like a jumble on top of each other here, but let's draw them up aside each other like this, using this what's called a density plot. So this sine function here is this function here, and so on, right? So these are the eigenvalues that come up here are actually square numbers. Now, you can repeat this for higher dimensions. So instead of having minus y double prime, you can talk about derivatives with respect to x and with respect to y. And let's take two of them like this with a minus sign as usual. And you can find the eigenvalues of this operator. Okay? And instead of having, since it's two-dimensional, instead of having an interval from 0 to 1, you can have, for example, a rectangle like this. Okay? And you end up with the eigenvalues of this rectangle, right, with this differential operator. These are the eigenvectors corresponding, this is one rather, eigenvector corresponding to this operator. Okay? As long as the region, this domain is bounded, as long as it doesn't go to infinity, you're going to end up with a number of eigenvalues associated with that domain. Okay, you can pick any domain you wish. For example, you can pick a disk, right? These are the eigenvectors corresponding to this disk, okay? And each of these has its own eigenvalue. And the nice thing about these eigenvectors is just as you can build up any function in terms of sine functions, so using the Fourier series, similarly, you can build any function of x and y on a rectangle in terms of these eigenvectors. Right? Any function of a disk on a disk, by any function, of course, there are limitations, you know, I have to be, you know, more rigorous in mathematics, but there's a wide range, let's say, of functions that can be written as series of these eigenfunctions. Okay? And also, for example, on a sphere, right? A sphere is a bounded domain. So you have a number of eigenvectors or eigenstates, as Professor Schwireb called them, representing each of these eigenvectors here, each of these functions has an eigenvalue associated to it, right? In fact, those of you who do a little bit of physics and chemistry are already familiar with these special eigenfunctions here. These are the electron orbitals around, let's say, a hydrogen atom. Okay? Of course, those are in 3 dimensions. But if you take a cross-section, or rather an intersection with a sphere, if you take those electron orbitals and you take an intersection with a sphere, you get exactly these functions here. So this will be, for example, the first shell. These correspond to the second shell, the third shell of an atom, and so on, right? This is the information encoded on the sphere, basically. And again, there's really no reason why you should restrict to any of these shapes. You can pick a torus, for example, right? And again, it will have its own eigenvectors. Okay? Any shape will do, actually. Any bounded shape, for example, like this one here, will have its own eigenvectors and its own eigenvalues. Right? Each of these functions has its own eigenvalue associated with it. And I know I'm going over time here, so I'll just stop with this last fact here. In the 1960s, there was a mathematician called Muscat who asked, therefore, this important question. And if each shape has its own eigenvalues, can you characterize a shape by those eigenvalues, perhaps? He tried a few examples, a triangle, for example, or a rectangle, and so on, and each shape had its own characteristic eigenvalues. So the question arose, therefore, can you perhaps identify a drum, that means an actual shape like this one, from its harmonics, okay, from its eigenvalues? Well, actually, no. It turned out later that there are what are called isospectral domains. Okay? There are shapes, such as these two, which are not the same, but which have the same eigenvalues. Okay? And this was obviously something that was quite a novel fact. If I can say perhaps something, one more step, I can do that, all right? The last generalization might be of eigenvalues, not on matrices and linear operators, but on nonlinear operators. Because, of course, nature is nonlinear most of the time. So it might make sense to generalize eigenvalues and spectral values even further to nonlinear operators. The first time they tried this was a simple extension of the eigenvalue equation, where you have f of x instead of a matrix times x minus lambda x is y. Like this, you try to find those values lambda, which make this impossible to invert. But later, I think more mathematicians are talking about this sort of model where you have a function f, nonlinear function f, where you have some input x and some output y, but you have some control, some parameters a. And then the idea of an eigenvalue is a special value of these parameters A, which give some kind of resonance, right? Some kind of non-invertibility. Okay, you all know what resonance means. Resonance, especially with a microphone, is what happens when you have little input but a lot of output. Okay, you have no input almost, but the whole system breaks down and you have that shrill sound coming out. Well, that's exactly what we mean by an eigenvalue. It's a special parameter for which this equation breaks down. And one way where this is being used a lot is the Navier-Stokes equation. This is, if you've heard about the Millennium Prize challenge competitions, right, where they have all those separate problems. Well, this is one of them. The idea is to try to show that this set of equations, which is a PDE, whether it breaks down in this sense, whether it has some kind of resonance inside it. Now, it's already too hard for, no progress has been made for a long time. So what people do is normally is to simplify this. So you say, let's suppose this U doesn't depend on T. So let's remove that term. And let's say this rho doesn't depend on T either. So let's remove that term. We divide by rho and we end up with this simplified version. Well, you can see the correspondence of what's written here with what's written here. The function x is this function u, this function y is this function f, and this parameter a is this viscosity parameter mu. So the question is this set of equations well behaved, or is there some specific value, well, probably mu equal to 0, where this equation breaks down? Whoever can answer that will win this, will win one of the prizes of this Millennium competition. All right, I'll end there. I hope you found it interesting, and I'll be open to questions.
It was very interesting, Prof. I think Prof. Shuirab has a question. He has his hand raised.
Yes, if you don't mind me asking. Joseph, when you're talking about these isospectral domains, is there something you can do to break the degeneracy? So if I deform the boundary slightly, could the spectra also change in an identical way, or is it just kind of basically is the degeneracy kind of a singularity, or is it a
yes, it has to be these specific. I don't mean these two specifically. I mean, there are many other isospectral domains. But yes, if you change, let's say, this one in one way, and you change this in a different way, then the eigenvalues change differently from one to the other. Right?
Okay.
So
okay.
It is kind of degenerate, like you're saying.
Okay. Okay. Fair enough. So you can't hear the shape of a drum, but you might be able to hear the shape of a drum if it's immersed in two different fluids.
But perhaps I should also say that, of course, this is stable in the sense that the eigenvalues will change only slightly. So I don't think you will hear the difference.
yeah. So fair enough. Fair enough. Okay. I had another question, but I completely forgot it. So, thanks.
It reminded me a lot of topologically protected ground states, which is kind of similarly to what Prof. Shuirab was saying. But I'll stop talking.
In the discrete case, we call them co-spectral. So we may have graphs that are non-isomorphic and give you the same eigenvalues. So you hear the same thing, but from different.
Yes, exactly. But in the case of matrices, if you have any two Jordan matrices which have the same diagonal, but you have different ones on top, they'll be isospectral, like you're saying. But the nice thing about this, what makes this even kind of different, is that these are both, how shall I say, these are both symmetric matrices, in a sense. Okay, this is
but symmetric matrices exist where they're co-spectral. And that's a problem of the isomorphism problem, no? Because we cannot distinguish graphs from their eigenvalues only. We need more and more information. So it's what you've been saying is very interesting, and some things were new to me, so nice.
I also have a question while Prof is mentioning graph theory, like at the very top where you started the reverse discretization sort of thing, where you made it finer and finer, not extended more rows. Is that related somehow? Because in graph theory, there's this idea of a graph on or a graph limit. I don't know if you've ever heard of it. It's basically this idea where the adjacency matrix gets more and more sort of, you know, n gets bigger sort of, and you get with like a shape like this. This is like how people usually visualize it. So the adjacency matrix looks like, I think of like a double bipartite graph, basically looks like a black triangle, a white stripe, and a black triangle down here, for instance. Like, are they related somehow?
I'm not, I don't know exactly, but if you, what I'm saying here, however, is I'm converting discrete
function of
columns into continuous variables.
Mm-hmm.
I'm not sure if that's what you're talking about as well.
Yeah, so it's basically the same, because the limit of a graph is like a function from like the unit square to, you know, 0, 1. So it's basically similar, right? It's like kxy.
Right.
Okay. I don't know if anyone else has any other questions for Prof. Muscat. Let me see. There's a question in the chat, maybe.
I'd like to definitely say that Prof.
Sorry,
Muscat,
I have
in
a
my
question.
opinion. Sorry, 1 second. He definitely wins prettiest presentation, in my opinion. I don't think anyone will top him. So and I'd like to say thank you. It was like a really nice talk, and I think you covered so many interesting bits and a lot of ground in such a short period of time. So thank you.
Thank you.
Very well placed, Prof. Also, one small question about when they're in 2D, these bases. Is it still like, what are the functions called, if you can like express them as a sum?
These ones, for example, here on a disk, they're called Bessel functions.
Oh, okay, all right.
These are actually quite simple. These are just sines times sines, basically. Sine x and sine y multiplied together.
But what do they call the class of functions which can be expressed as sums of these?
It would be L2. L2 on
L2,
whatever domain you're talking about.
Okay.
In general, these are called harmonic functions, kind of as a generic name.
Mm-hmm.
Especially the fact that every function can be written in terms of harmonic functions that has a whole theory behind it. Okay? And generalizes basically Fourier series and so on.
Like harmonic analysis.
Yes, of course. Harmonic analysis, in fact, is the whole topic.
I think someone else, I interrupted someone's question.
Yes, Professor, you mentioned that the derivative operator is like complex. In what way is it?
Well, I can easily show you why d squared is negative. I don't want to take that much time, however. Let me see if I can. Let me stop this share here. Y double prime, or rather, I wrote somewhere that D2 is negative. In what sense do I mean that? Well, if you take the integral, well, let me, what do we mean when we say a matrix is negative? A matrix, we say that a matrix is negative if when you input vector x and then you dot it with the same x, then the answer is always negative. Okay, this is what we mean by having a matrix being negative. Now, when you generalize this to infinite, to the continuous case, what we mean is you have two derivatives on a function and somehow take the dot product with that function, you get negative. Now, what is this dot product? It is the integral of y double prime. Like this, okay? Let's say between some limits, all right? Then using integration by parts, you can transfer one derivative to the other side, and you end up with minus y prime times another y prime. Now, y prime squared is always positive, obviously, and they have this negative sign, so this becomes negative, right? So you can see that this is always negative, right? Whenever you take two derivatives, because of this integration by parts, you end up with something negative, right? So in this sense, a derivative operator is kind of like an imaginary number because its square is negative.
Right. Thank you.
Okay, so yeah, I think thanks again, Prof. That was very interesting. I mean, like Jake said, you put a lot of stuff in like a surprisingly short amount of time. It's impressive. Thank you. So now we'll go on to Prof. Shriha's talk. Good day, Prof.